Hello, it's dumplet here. Here's an item on algebra. Find all real ordered pairs xy such that x raised to 2004 plus y raised to 2004 is equal to x raised to 2005 plus y raised to 2005 is equal to x raised to 2006 plus y raised to 2006. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Now, essentially, this equation is going to give us three different sets of equations. So I can say that, okay, these first two belong to the first equation, the second and the third forms the second equation, and the first and the last forms the third equation. So this should be more than enough to help us get the values of x and y. Now, I'm going to split this into two. So the first one, I'm going to compare the first two terms, and then the second one, I'm going to compare the first and the last. And I will be able to get two equations from here. So from the yellow one, I'm going to manipulate this a bit. I'm going to put the x's to the one side, to the left side. All right. And then the right side becomes just a place for the y's. All right. And I see that, okay, I could factor whatever I could factor. So that's my experimenting phase, I guess, of the question, and that's what I got. I realized I couldn't do anything further, so I decided to take a look at the second equation that I could form, comparing the first and the last term. Similarly, I put everything to one side, so x raised to 2004 minus x raised to 2006. That's equal to y raised to 2006 minus y raised to 2004, and I could do the similar factoring. And I'll have a 1 minus x squared here, which can be factored further into 1 minus x, and then 1 plus x. And then similarly for the right-hand side, I'll be left with y squared minus 1, which can be factored further into y minus 1 times y plus 1. And there's a bit of similarity here because the second part, the second equation does involve terms involved in the first equation. So that's going to be something that we could ponder upon because, well, we have this common part, so that should imply that, well, 1 plus x is equal to y plus 1. And that's correct, provided that these two underlying terms, they are not equal to 0, right? Because we can't divide by 0. So if we make sure that they're not equal to 0, then we could have this relationship, and right, I guess I can easily get that x equals y from there. So let's just take it case by case. So we have two cases actually. The first case is, well, if this part is equal to 0, then, well, that part must be equal to 0. And I'm just going to solve for the x and y. Oh, sorry, this should be a 0 equals 0 equation. That's what I meant to say. So if the first one is a 0 equals 0 case, then I could easily solve the values of x and y. I would just solve them individually. But if it's not a 0 equals 0 case, then it's going to fall under the second category because, well, these two are not equal to 0. I can cancel them out, so I'll just be having this part, which is very simple because I'm just going to get x equals y from there. So just summing up all the things I've mentioned, we have two cases. So case 1, where this entire thing, it's a 0 equals 0 scenario. So what I have to do is just solve for x when this is equal to 0, and then solve for y when this is equal to 0. And that's not too difficult because it's already in the factored form. So I have two possible values of x, 0 and 1, right? If it's 0, then this term would be 0. If it's 1, that term would be 0, and no other values of x. And similarly for y would be 0 or 1. Now, obviously, I could pair up the x and y. So technically speaking, I'll have 4 solutions from case 1. 0, 0, 0, 1, 1, 0, and 1, 1. And everything else is going to be part of case 2. So if for the case of case 2, we're going to have 1 plus x is equal to y plus 1. And this part is just going to give us x equals y, which we could substitute into the original equation. Now, let's just say x and y, they're both equal to a certain real number k. All right. And if I do that, essentially the equation becomes 2k raised to 2004. That's going to be equal to 2k raised to 2005. That's going to be equal to 2k raised to 2006. And just like the reasoning at the start. Essentially, I do have 3 equations here, but I'll just focus on the first 2. Now this will be sufficient. You guys could always check all the other possible pairings, for example these 2 and these 2, but you guys would be able to see that this method that I'm using, it's going to suffice. So I'm just going to focus on the first 2, and I'll be solving for k here. I could cancel out the 2 because I could, because 2 is not 0. So I'm going to move everything to one side. So k raised to 2004 minus k raised to 2005, that's going to be equal to 0. Factor out k raised to 2004, so times 1 minus k, that's equal to 0. Now, solving for k, I get 2 values. K is either 0 or 1 and no other possible values. And since x and y are both equal to this real number k, that corresponds to having 2 solutions, 0, 0, and 1, 1. Apologies for that, 1, 1. And I guess it's pretty obvious if I substitute it back in. If I put 0, 0, then everything here becomes 0, so the equation is correct. And same is the case if I put both of the values to be 1. So it's going to be a 2 equals 2 equals 2 equation. So these two solutions indeed works. And although we got 2 solutions, but they don't really add to the 4 solutions already had, or we already acquired from case 1. So logically speaking, we've already exhausted all the cases. We only got 4 solutions, so these 4 solutions will be our final answers. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye.